In 2018, the NCEA question using Hess's law was particularly difficult, or at least it appeared so on the surface. Luckily, the information that was given to you was actually given in a very good order, that you just had to follow the order that those equations were given to you, and enthalpy values. So what we're trying to find is the enthalpy of formation of this chemical here, Al2Cl6, in its solid state. And it gives us everything in purple here. There's something that doesn't quite fit in the screen, sorry, there we go. So it gives us these 1, 2, 3, 4 equations and their enthalpy changes. And we've got to somehow put those together to come up with an equation that has 2 aluminiums as a solid, 3 chlorine molecules as a gas, and Al2Cl6 as a solid. So looking at those equations, that looks quite tricky. That's why I'm doing this one. We approach this question in a slightly different way to the previous one. We're actually going to work with the equations and the enthalpies together. So my first thing is to go, okay, let's have a look at the aluminium. Does one of them have an aluminium in it, or even better, 2 of them? And it does. This equation has got aluminium in its solid state already as a reactant. So I'm going to copy that one down, and I'm going to tick my aluminium off and say, right, I've got that one. Now it introduces a whole lot of things I don't want in the equation, so my next job is to try to eliminate those while at the same time building the rest of my equation. My personal approach is to try to build the original equation, so these 1, 2, 3 different chemicals being in there, see what cancels out, and then see if there's anything left over that I have to get rid of. I'm hoping the fact I've pre-done this on my whiteboard makes it easy enough to follow, but I'll try and explain every step, and I've used colours to try to show what I'm talking about. So the first thing I did an equation that had 2 aluminiums in it, and that's my first one there. There's no need to change its enthalpy for this because I've just used the equation as it is. Next up, I need to put 3 chlorine gases into my equation. So that's my next one. I'm going to take the equation with chlorine in it, this one here, and I'm going to multiply it by 3. So I get 3H2, 3HCl, and 2 times 3 is 6 HCl's being made. So 3 hydrogens, 3 chlorine molecules, 6 HCl molecules. Again, I've introduced something that I don't want. And then what I'm going to do is I'm going to cancel some things out. This has introduced some hydrogen, and it is in the gaseous state, so I can eliminate these hydrogens here. So I've crossed these 2 off. I can't cross out my HCl's because their state of matter is different. There's a bit more going on there. Luckily, we've been given an equation to do that, and I'm going to do that last. The last thing I want to do here is I want to get Al2Cl6 in its solid state introduced, and I need one of those. Now I know I've got Al2Cl6 in this pink equation, but it's in the aqueous phase. That's not correct. So I need to turn it back into its solid state. So I've got my 1 times this equation, 3 times this one. This equation is written in the opposite direction, going from solid to aqueous, and it's exothermic. I need it to be the other way around. I need the solid to be my product. I need it over here. So I need to go from it being a reactant to being a product. So I flip the equation over. In doing so, I take it from being negative 643 to being positive 643. Exothermic becomes endothermic if we reverse it. Now, that's convenient because that's given me an Al2Cl6 that's aqueous, and it's there as well. I can cancel these ones out. I'm sorry, my red and my orange are quite similar here, I've noticed. Not so similar on my whiteboard in person. So that red crossing out is showing where the red equation has got rid of it from this one. So now I've got this, and I've got this. That should be it. But it's not. I've still got some HCl aqueous in here and some HCl gas. They don't cancel out because they're in different states of matter. This is where this question was quite tricky. So I've got to use this equation here, the HCl gas to HCl aqueous, and luckily they've done it the way that it's easiest to use to get rid of both the aqueous and the gas HCl molecules. So, if I have 6 of that equation, it'll give me 6 HCl gases as a reactant. That means I can cancel it out with that one, hoping the blue and the blue shows that. And it makes 6 HCl aqueous. Well, that can cancel out those ones there. Now I'm only left with the things I've got the ticks next to. This is 6 of that equation, so I've gone 6 times negative 72.4 to give me 434.4. And then I'm just going to add up the numbers that have got a box around them. I'm also going to add up my equations to check that I have actually got my original equation, that I've cancelled out everything I need to, and then I do that sum and I get negative 1,346.4 kilojoules per mole. In NCEA, we tend to work with 3 significant figures, so I'm going to round that one off to negative 1,350 kilojoules per mole. This one is about as hard as they get in level 3, and similar type equations are often asked in scholarship. So if you can do this one, you've got a really good understanding of Hess's law, and you should be able to answer any question that you're given in an exam where you have to apply Hess's law. So just a reminder that when I looked at this equation and it looked pretty complicated because it gave me all these other equations, all I'm doing is I'm trying to find, well, what gives me 2 aluminiums? What gives me 3 chlorines? What gives me the solid version of Al2Cl6? Some I'll have to reverse, some I'll have to multiply by a scalar or by a number. But ultimately, I put it together and things started cancelling themselves out. That's one of the beauties of Hess's law. Things start to cancel each other out. We just check it at the end that it's done everything we had to. And then if it has, we add up our enthalpy values and we've got our enthalpy for that reaction.